Welcome to this presentation of the Rotary Club of North Bethesda, Maryland, USA. Our club was established in 1974. We meet every Friday morning at 7:45 a.m., and we often invite guest speakers to give presentations on all kinds of interesting subjects. Please contact us through our website at nbrotary.org. And thanks for watching.
Show here. Not too many pictures, but you've probably all seen some of the news about this new telescope that has been placed about 1 million miles from the Earth in a special orbit, and it is going to be you'll be hearing a lot more and seeing a lot more pictures from this in the near future. The James Webb Space Telescope. Now, James Webb was a NASA administrator back in the 50s, and I guess it was named after him because he was a great fundraiser and politician as well as a scientist, and he's been celebrated for his amazing achievements that got NASA going in the early days of the Apollo program. So the telescope is kind of strange looking. It doesn't have a tube. It just has the mirror and some other mirrors. And it's behind the mirror is a box of instruments, including cameras and spectrographs analyzing the light from the distant space. And this awkward looking thing below the mirror is a sunshade, and it's made out of 5 layers of reflective plastic that help to keep the mirror cold. This whole telescope is designed to work in the infrared part of the spectrum where it's very cold. It has to be kept cold in order to see the stars, the infrared light from stars. So they keep it cold down to about over 300 degrees below 0 Fahrenheit. So, you know, when we look out at a room or at the stars, we are seeing only the visible light part of the spectrum. The spectrum is the range of electromagnetic radiation that goes from 0 to infinity, basically. It's all these wavelengths. We call them different things, but they're all basically the same except for the wavelength. So light covers less than an octave. If you were to convert them, those light colors into notes, they're less than an octave of notes. So I have my own notes here somewhere.
Paul, should we be seeing a picture? We don't see a picture.
Oh, you don't see the picture. Okay, stand by. I have to share my screen first. That would help. Mess up your computer. All right, there. Okay. You see that?
Yes, we do.
Okay. So there's the telescope. And I'm just going to go through. I was showing this slide that shows the piano keys. And so if you say middle C is in red, we can see only about an octave of light. But the James Webb Space Telescope can see, so we can see these 3, basically our retina has 3 different pigments, so we can see this range of colors, red, green, blue. But the James Webb sensors have many more octaves of frequency range down to the low notes. In fact, it goes way beyond the piano keys down to the lower frequencies or the longer wavelengths. Now this diagram shows the place of where the James Webb Telescope resides, the infrared, from the near infrared, which is near the visible light, and all the way down to 28 microns, which is a long way into the mid-infrared light. Now, there's also a space telescope called the Spitzer, which goes to longer wavelengths, but it's much less resolution than this James Webb telescope. So now, in terms of just about thinking about space, this is the Voyager spacecraft, which was launched in 1977. And I've been interested in this. I followed this Voyager for my whole adult life, as it took a grand tour of the planets going from Mars, Jupiter, Saturn, Uranus, Neptune, and then on its way out of the solar system completely. And it's now beyond the range of Pluto, beyond the solar system. So that's basically in a lifetime. That's as far as it could get. And so at the current speed of 34,191 miles an hour, Voyager will reach the distance to our nearest star in about 80,000 years.
Wow.
The nearest star is about 4.2 light years away, Proxima Centauri. And that's just to give you an idea of the distances. And that's an average distance for stars, I guess, in our galaxy. So space is big. That's what we're seeing. And it's far beyond our ability to really comprehend. Now, this is the first picture from the James Webb Space Telescope that was released to the public last month, and with great fanfare. And there's a collection of just a handful of pictures of various things that they released in this early distribution of pictures. So what we're looking at here is a part of a nebula in the constellation Carina, which is in the southern hemisphere. And you see some features. I want to try to describe what we're looking at here. Now, this looks like a really thick dust cloud. It is a dust cloud, but the scale, if you see on the bottom, the line on the bottom shows the scale. It's about 2 light years. Let's see if I can make this a little bit. Yeah. See, that line is 2 light years across. So we just talked about light years, you know. So a light year is about 6 trillion miles. So when you look, the dust actually is very thin. It's thinner than our air. But if you put a light year's worth of air together, it would be pretty opaque to light. And so the glow here is caused by fluorescence of this gas, which is mostly hydrogen and helium. And so it radiates some light, and it's also reflecting the light from the nearby stars. Now, with the James Webb Telescope, the stars show 6 points because there were a tripod of 3 bars that were supporting the mirrors. So, and you have this hexagonal set of mirrors that were put together. So it shows 6 spikes. Hubble telescope pictures show 4 spikes, so you can always tell the difference, which kind of telescope picture you're looking at. The light from the stars, the ultraviolet light, is lighting up this gas and causing it to glow. And that's why we see these nebulae have a lot of beautiful patterns and pictures. So you've probably seen a lot of these.
How long ago was the pictures, you think?
How long ago?
No, it's light that's reaching us from a long time ago.
Well, this Carina Nebula is 7,600 light years away. All right, so that's within our galaxy, but probably about a quarter of the way around.
But the light that we're seeing came from like
7,600 light years. Yeah,
So that's 76. How many years ago was that?
7,600 years ago. Yeah.
We're
It
seeing
travels at the
fast.
speed of
We're seeing
light.
fast.
And so when you're looking at something that's far away, you're looking backwards in time. And so any of these telescope pictures are like a time machine. They're looking back into the past. So if you're looking at light from 1 light year away, it's 1 year old when it reaches your eye. But we'll see some things that are a far longer distance than that. This is another picture. This is from the Hubble telescope. This is a wider angle view of that same nebula, Carina Nebula, showing all the crazy things that are going on here. I noticed, for example, here's up in the upper right is a new star that just formed, and it's shooting out jets left and right sides. You see a lot of strange events happening. Here's a close-up view of one of those stars. It's the mass of dust and gas has coalesced to the point where the density at the center reaches a certain level, and the heat is high enough, several million degrees, that it begins the process of fusion like a thermonuclear bomb, and that's what forms the star. So this is a star being born, and it has a ring of dust around it, which ultimately will become planets orbiting the star. And sometimes some of the material falls into the star itself, and it spins and it shoots it out as a beam in both directions.
Excuse me, Paul.
Yeah.
The star that you're talking about, that would be similar to our sun.
Right.
Okay.
Right. Our sun went through this process about 4.6 billion years ago.
And what is that dark area below it?
That's the dust cloud that's surrounding the
Okay.
star.
Okay.
And it's gradually condensing into planets. So now here is an interesting set of data. This is another new release from the James Webb Telescope. It's a spectrum, an analysis of the spectrum of the material in the atmosphere of a planet going around another star. And this was this was just recently released information that shows that we detected water vapor and carbon dioxide in the atmosphere of this planet orbiting around another star, maybe 1,000 light years away. Okay? So that shows the incredible power of this instrument to be able to
How fast
answer things like that.
that picture we just saw of the star being formed and
Yeah.
that whole process takes billions of years. Okay? That way it looks like a still picture, I guess, right?
Right,
So
right.
slowly.
So it's a very tricky matter to try to understand how we analyze these things.
I have another question, maybe I'm interrupting too much, but wondering if, can we see reflection of our own planet on these planets or the entities out in space that can sort of reflect our path?
No.
That's an idea,
No.
right?
The star, now here's a diagram of how they do the tricks to analyze this atmosphere of another planet on another star. Okay, keep in mind, we're looking at a star which is so far away, all the stars are just pinpoints of light. They cannot be resolved into a disk. Right? They're just pinpoints. They're just so far away and so small relative to the distance. So they do a trick. They look at the light from the combined dot, the little point of light, and if there's a planet there that happens to have an orbit near that crosses the star, then it drops the light from the star by about 1%. And dims light. That's how we know there's a planet there. It just dims the light a little bit. We can't resolve any pictures. We can just see the light gets dimmed a little bit. And when it's just starting to come across this and block the light, there's a little tiny zone of time where you can analyze the light and find the spectrum of the atmosphere of that planet before it blocks it out. So that's what this is about. It's a
Paul, has water been found on any other planets or stars?
What?
Has water, H2O, been found elsewhere in the universe?
Yes. Yes. H2O is pretty common. Methane, CO2, a lot of these simple molecules are being found now.
So with the
There'll be
different
a lot more research on this in the future. I have a few more slides and then I can take some more questions. Okay, I just want to move on through these to make sure that you get a chance to see these new pictures, and then we can talk about it. This is a star that's in its dying stages, and it is shedding layers. It has blown off several layers of the outer layers of the star, and this is called a planetary nebula. It really has nothing to do with planets. In small telescopes, they look like planets. They're little round things. But it's a star, and as you can see again, the light's quarter of a light year across, something like that, about half a light year across. So it's an enormous explosion that's ongoing from this star. There's a star cycle. We've been able to piece all these things together, and the cycle goes like this. It starts with a nebula of gas, which condenses to form these stars and planets. Takes a few million years. The star burns. Stars like the main sequence stars like our sun are long lasting. They'll last 5 to 10 billion years at a fairly stable rate, and then finally they begin to expand and shed their mass, and they could, if they're big enough, they could explode in a supernova. So that only takes a few seconds. And then what happens, the supernova blows out all this gas and dust and whatever, and that forms the nebula, which can make new stars. So that's the star cycle. So with that process, this is an example of stars in our Milky Way. So when we look through the galaxy, this is within our own galaxy, and we can resolve all these stars. And you see they have different temperatures, which are different colors. That's from the Hubble. That's not the James Webb. That's a Hubble photo. This is another picture from Hubble of it. This is a galaxy. Typical spiral galaxy like ours, looks similar to this. Our own star, our sun, would be somewhere around the outer arm of this galaxy. And galaxies typically are about 50, 60,000 light years across, contain a few 100 billion stars. This particular one is relatively close, 23 million light years away. Now this is a picture from the James Webb. This is a new picture of some galaxies. This is called Stephan's Quintet because it has 5 galaxies. Actually, there's the one on the left there is relatively close. It's not related to the group, but the other ones are interacting and they're throwing stars off to their side. You can see some of the stars getting spun off over toward the left, and they're swirling around, interacting with each other. There's a big black hole in the middle of the upper galaxy that is also interacting with the nearby space. And in the background, behind all those stars, you see there's a lot of little spots. Those are not stars. Those are other galaxies. Okay. So you could think of this picture that has a lot of depth. That bright star that has 6 points, it's like nearby to us. It's in our galaxy. The cluster of galaxies, if you think of this as, say, those would, if you scale it, so those are like in your house, your neighbor's house next door to you, then the distant galaxies are like in the next town over, right beyond that. So we we have a hard time telling distance with these things, but there's a tremendous range of depths of distance in these stars. Now, this is another new picture from the James Webb Space Telescope, which is, to me, the most interesting by far, and is showing a galaxy cluster in the center. There's 3 or 4 very bright stars which are very near us in our galaxy that show the 6 points. And then in the background, you see all of these other little spots, most of them kind of oval shaped. Those are the other galaxies at great distances. And you can begin to see, if you look carefully in the middle, a lot of these background galaxies appear to be bent or curved, little arcs. You see that? That is due to the force of gravity from these big galaxies in the center that is warping space-time so that it looks like the light is being warped and bent from these distant galaxies behind it. And so it's called a gravitational lens. And that, again, that can be used to calculate the distances to these distant galaxies, and sometimes the lenses magnify so you can see a lot farther away than you could otherwise. So this is called a deep field, where they will expose the camera for a long period of time to soak up light from these very distant galaxies in space. And so what's of interest to me also is they have spectrographs which can take a look at any one of these spots and analyze the composition of the light, the elements that were causing light. So this diagram shows how they can look at the frequencies of light that come from each of these galaxies, and they can determine what the composition was, and also using the redshift effect, they can tell how far away they are directly by measuring their redshift. So they're going to be doing a lot more of this kind of analysis with the Webb Space Telescope. This was just a tantalizing sample of a handful of these pictures of various things in the universe, from nearby nebulae out to the most distant galaxies, going out to billions of light years. So the longest one they have here is 13.1 billion years, 13.1 billion light years distant, the age of the universe is 13.8 billion years. So we're within a billion years of the age of the universe, and this is the kind of data we'll be getting a lot more quantity in the future, but the quality is really impressive. So this gets into cosmology. Now, when you get to a collection, this is like a simulation that was made to get a sense of what does the whole universe look like at the largest scales. So if we start at, this is like a galaxy cluster, one of those dense clusters. And if we start with this and then zoom out to even bigger scales, it might look something like this. This is kind of a simulation, but it'll give you an idea of what the large scale structure of the universe looks like.
Wow.
So this is what's called the cosmic web. Dark matter and gravity has pulled the mass together into kind of threads, and in between those threads are big voids, empty space, and that space is expanding at a rate described by the Hubble constant. And so the universe at larger scales would look like this.
Looks like a sponge to me.
Yeah, like a sponge. So that's my last slide, and
Paul,
Okay.
where is the Webb satellite telescope right now? Where is it in Texas?
where is it? It's located at the Lagrange point, about 1,000,000 miles behind the Sun-Earth line.
In orbit around something?
It's, yeah, it's in an orbit.
Around what?
Yeah, it's
Around the Earth?
no, it's not around the Earth. It's like more like parallel to the Earth, going around the Sun.
Our sun.
Hmm?
Our sun.
Yeah,
Our Sun.
We haven't got that far.
Yeah.
Right.
May I ask
It's
you
never
a
mentioned
question?
in the
Okay, cool. Sorry, maybe it's a very primitive question. You show a spectrum, what, picture was done in space. And they send picture here, but we can see from this picture just part of it because our eyes, smaller spectrum. Who can say this is exactly what it is? It's translated or how?
Yeah, there are sensors, there are instruments that are sensitive to other wavelengths of light that we can't see. And for example, a radio is like a long wavelength sensor that is detecting light that we can't see. If you think of light as just electromagnetic radiation, it includes radio waves, TV, Wi-Fi, Bluetooth, microwaves, X-rays, gamma rays. It's a wide spectrum of things. We have different names for them, but they're all the same except for the number, the wavelength. And so there are instruments that have been invented, like radios, to detect those different wavelengths.
My question was, technology, it's a lot of options, it's a very good one. And they send picture, and we can see this picture, but we can see just a little bit, from what is it, like a Inca, some calendar, people look at this.
Right.
Can understand. So about, all this spectrum, I'm afraid, if they send picture from, we cannot see with our ability what it is.
I don't understand.
No.
I think what she's trying to say
Yeah.
is, I think, is how do you, you're showing us pictures that are within the light spectrum. But these are pictures from the light spectrum, this is how the instruments
Yes.
are converting the light that we cannot see.
That's right.
Into something we
That's
can
a trick that NASA does. They take the sensor results, which come from different filters, and they are electronic signals. And so they can make them any color they want, right? So they typically will make shorter ones blue and longer ones red. Just so that they squeeze, so that they push it into our spectrum, so we can see it.
Yeah, how do you, the spectrum is so wide.
Yeah.
So how do you convert, if you look at one picture that's blue,
Yeah.
they made one part of the spectrum blue, but then if you look at another spectrum, which is a totally different part of the spectrum, the blue there would be a different.
Well,
spectrum.
if you can see here, let's see, I'll share screen. This picture, for example, shows, let's see if I can. I don't know if you can see, but down at the bottom here, you see these little numbers and colors?
Yeah.
Those are the filters that were used for this particular picture. And it shows they're different colors. They're just indicating these different filters were translated to these colors so we can see them.
That's sort of like the
Yeah.
guide to interpreting the colors and know what spectrum
Yeah.
you're talking about.
Another way of raising the same concerns is to say that we better be careful so we don't get this mixed up with reality desire. This is what is produced by our adopting certain assumptions. we're going to follow this. We're going to be looking at light as the key to understanding the world. That's a pretty arbitrary assumption. Arbitrary, not in the sense that it's scientifically reckless or anything. It's very disciplined, very scientific. But the scientific approach as such avoids an infinite number of variables that are simply not caught because of the method that we're using. I mean, Steve brought it up in one way and Victoria in another. And yet, it's built into the modern consciousness that what science, in this particular sense, is giving us is reality. It's not reality, it is what results when you apply a certain methodology. It's like, you know, glasses we can buy with different properties. We don't see, we're not blinded by the sun or something like this. Well, science is like that. Pick up these glasses, not those for those and those for those, and what results is marvelous. And we get a kind of grasp of what is going on, something very orderly and strange and so on. But it's not reality. It is what we have found out so far by using this very selective method.
Well, I agree with you. It's, I'm not really, didn't intend to get into philosophy of science, but I appreciate your.
No, that's what I agree with you.
I agree with you, okay? I didn't say this is reality. This is a slice of a
Right, I think
aspect, and be happy to have it talk about that.
Scientists have to acknowledge that their own viewpoint is going to affect what they see and interpret. And they're putting light to the spectrum and arbitrarily attaching it to that so that we can see something that we can interpret.
Yeah.
I think that a good scientist will know that that's what they're doing and realize that, you know, there could be something off to the way we interpret it and, you know, keep thinking out of the box in that sense. But you have to have it, I guess, for people, for humans, you have to put what you're doing and what you're seeing, what you're experiencing in some kind of context that you can understand in order to move forward from.
Yeah, and what I'm saying is that science, in one sense, is very soft. It's not hard. It's squishy soft.
Well,
It's very useful, but squishy soft.
Well, they present the actual facts, the spectrum itself, and what they're presenting is a bit of an interpretation of that spectrum. So the people looking at what they're doing have to understand that. It's all an interpretation, right? Okay, we got 8:30.
You mentioned one of the slides that you mentioned, is a water vapor, also carbon dioxide and methane. So is it possibility that the life, because of the components that you just mentioned, 3 of them, components are the part of life in general. So are there any kind of predictions that there is life in that particular area? Life.
Life? Okay, so clearly, with looking at the atmosphere of these planets, that's the implication. Where can we find evidence for life on other, maybe other planets? So that's one of the big questions that we have, obviously. And there are certain kinds of compositions of atmospheres that are good clues for life. For example, presence of a lot of free oxygen would be an indication that.
Or if they detect smog.
Yeah, air pollution. Right.
Or or a signal.
All right, thank you, Paul. Very interesting.
I'm even a squishier science, I'm in psychology.
Oh, because you were, I thought, prompting.
Yeah.
And I guess you've heard this